All right, welcome everyone. Thank you so much for joining us today. I hope everyone that joined was able to see those first few reminders when you first came on, just to make sure that you keep your microphone muted. I want to thank you again for joining us this afternoon. Again, my name is Kelly Hill, and I am the Green Growth Specialist for the Georgia Coastal Management Program. Our program is housed at the Department of Natural Resources, Coastal Resources Division, and we're located in Brunswick. My coworker, Jennifer Klein, is also joining us today, and she is our Coastal Hazards Specialist. I'm going to provide a brief background on the project that you'll be hearing about before passing it over to our research partners. All right, next slide. For those of you not familiar with our program, we participate in the Federal Coastal Zone Management Program, which is administered by NOAA, and this makes us eligible to receive federal funding for program implementation. We have an 11 coastal county service area, which you can see on the next slide. And our work involves many networked programs and initiatives, as can be seen here. And one of our primary roles is to provide technical assistance to local governments, partner agencies, academia, and the general public on coastal issues. Next slide. The project being discussed today came to fruition through one of our program assessments, which is required by NOAA, where we identified needs and gaps within our program for addressing coastal hazards and community development issues. With funding from NOAA, we have developed and nearly completed a 5-year strategy to address these needs through our project titled Enhancing Coastal Resilience with Green Infrastructure. The primary goal of this project is to demonstrate how a coastal community can become more resilient to riverine and coastal flooding and wind events by implementing green infrastructure practices. And for the purposes of this study, green infrastructure was defined as practices that enhanced infiltration and retention of rainwater for inland riverine flooding scenarios, as well as dune enhancement and policies such as shuttering ordinances for mitigating coastal flooding. Next slide. Next, you're going to hear from our research partners that conducted the extensive data collection and modeling of different flooding scenarios and their associated economic impacts. And then as I wrap up towards the end, I'll provide more information on where you can find additional guidance and resources that are related to this project, as well as learn about some additional training opportunities. So with that, I would like to introduce our research partners. The research for this project was supported by teams of experts at both the Polis Center at Indiana University, Purdue University, Indianapolis, and with the University of Wisconsin's Space Science and Engineering Center. Both organizations are nationally recognized leaders in hazard risk modeling. For today's presentation, we are joined by Kevin Mickey with the Polis Center and Dr. Shane Hubbard with UW Space Science and Engineering Center. And with that, I will turn it back over to you, Shane.
For attending. I'm Shane Hubbard at the Space Science and Engineering Center. I'm a research scientist there. And our center specializes in doing hazard risk modeling for places all over the globe. And in particular, we do a lot with remote sensing. There's not a lot of remote sensing in this project. We're doing a lot of geospatial analysis using other models to help identify communities at risk and areas at risk along the Georgia coastline. And Kevin Mickey is a partner in this, and Kevin has a long history of modeling and doing similar geospatial analyses at IUPUI at the Polis Center. So I'm going to get into a little bit of introduction of the project. We have noticed, along our streams and rivers and along our coastlines all across the United States, some early signs of climate change. Here's an example of a high tide where we have some areas that have been inundated that probably weren't at this level in years past. This is the, I think, causeway that goes to Tybee, and during king tides, we see that sometimes this road is overtaken with water, during king tides especially. But this isn't the only place along the Georgia coastline where we're seeing some changes as a result of sea level rise, but also increased storm surges and sometimes storms that are causing the water levels to rise at different levels than they have in the past. And then Fort Pulaski, Georgia represents one of the longest histories we have of monitoring the sea level. And thankfully, it's right there in Georgia, along the Georgia coastline, anywhere in the United States, and has a record back to 1935. And this is just a figure that's showing how the sea level there has changed over time. and then the results are some of the things that we're modeling as we go into the future. So how do Kevin and I and the research teams that we work together, what is our goal? Our goal is to engage the community by taking a look at some of the modeling and geospatial modeling we're doing of their communities related to flooding and hurricane winds within their communities, bringing that back to the community and talking about solutions. How can we potentially mitigate against these hazards that we're modeling through mitigation projects, through resilience actions, so that their communities are resilient going forward in the future. We then always bring the education back to the community, talk to them about how we did the modeling, what do the numbers mean, how can you then use the information going forward, and trying to educate the community on how we've put this information together. And then come up with best practices. What are the things that are going to be best utilized to help mitigate these risks into the future? What are things to do today? What are things to be thinking about as you grow as a community going forward? So in phase 1 of the research, there was an initial hazard assessment along the Georgia coastline, and we collected some data for hazard and building data there. And what we learned from that research, we brought into the phase 2 piece, where we looked at current hazards and risks to the Georgia coastline. Then we looked into phase 3 after what we learned in phase 2. We looked at what could we see for potential changes into the future as a result of future climate changes, but also just changes to our communities. Communities will be growing, and so the changes in those growing communities, things like impervious surfaces, what would that impact in terms of our streams and rivers and along our coastline? And then possible next phases would be extending this to other areas along the coastline and maybe looking at some other scenarios with respect to future climates. So how do we perform these analyses? These are geospatial. What's great about these being geospatial is that we can actually bring to the community, where are these hazards? Where could they potentially be growing into the future? What is the depth or the magnitude? What's the wind speed that we want to be concerned about? And we can also look at the sort of heterogeneous, or the areas that might be differing across the community in terms of the risk. And so you may have communities that are at more risk than other communities, maybe by the way their buildings are constructed or how high those buildings are elevated within a floodplain. We generate economic loss and social impact assessments from the geospatial hazard assessments that we do. We can do that with floods, earthquakes, hurricanes, tsunamis within a program called HAZUS-MH. And so HAZUS-MH is one of the tools that we use. It's a piece of software put together by FEMA, and it's one of the pieces or softwares that we use, but we use other geospatial techniques in conjunction with HAZUS to help us understand what the risks are along the Georgia coastline in this project. One of the things with HAZUS-MH is you can use hazards coming right out of the software itself, or you can create or generate your own hazards external to HAZUS and bring those in. Also, in order to really understand the full risks to a community, you have to understand a little bit more about what's impacted. So the buildings, the people, and so you can also use your own information on buildings and people and bring that into HAZUS-MH. So, well, what is at risk? Well, certainly we understand buildings would be at risk, and infrastructure, the environment can be at risk, and also populations. And so when you're wanting to describe what's exposed to a hazard, you really want to know the questions you're asking, the availability of the data, and the capacity of our modeling tools and techniques. So for this project, we really focused largely on the buildings and infrastructure because we have very, very rich data along the Georgia coastline for those two aspects. And also the relationships between flooding and wind and how those impact those two. And also we looked at populations for our project. So how did we create our buildings for this project? We used CAMA data. So this would be data that we often get from a county assessor within a community where we are tracking buildings and properties throughout the community, and we can grab building characteristics from that data. So we also have to then locate those buildings in space. And so for some communities, you may only have a parcel footprint or the land footprint footprint, of the land ownership footprint, whereas in other communities, you may be able to locate that right and directly on the building. And so from this information, we can get things like the name of the building. So maybe this might be a gas station, or it could be a grocery store, restaurant. The occupancy type, single family residential, the number of stories that the building has, and then of course the replacement cost. So in order to fully understand how damaged or the impact a building, the impacts to any particular building or group of buildings, we have to have a little bit of understanding about the building itself in order to understand what the full impact will be. So in phase 1, we looked at all 11 coastal counties together, and we had 3 different scenarios involved. We looked at a Cat 2, Category 2 hurricane, a Category 4 hurricane, and a Category 5 hurricane. The Category 2 hurricanes and Category 5 hurricane followed the red path that you see in the image to the right. That path simulates very similar to how Hurricane Andrew approached Florida in 1992. The Category 4 hurricane is the blue line, and that at the time was mimicking Hurricane Floyd's path. But as we know, actually, we've had a number of hurricanes here. When we started this project back in 2016, well, actually earlier than 2016, we hadn't had Hurricane Matthew or some of the other hurricanes that we've had since then that have followed a very, very similar path. The blue path represents a worst case scenario for the Georgia coastline. And the reason it's a worst case scenario is because every single coastline community would be impacted in a very, very similar way, because it's basically kind of raking the coastline. Whereas with the red path, this is a more direct hit. And so the communities are going to be impacted differently. Those communities closest to the path would be impacted the most. Those communities away from that path would be impacted less. And so we wanted to get a mix or a range of scenarios so that we could take a look at what those impacts would be from those varying storms. So one of the things that we ended up doing with the analysis is we wanted to look at the hurricanes themselves just in a current state, but then looking at those hurricanes if we were to have something with sea level rise and a slightly more intense storm. And so if you look at the top one says worst case maximum impact, and these are the dollar losses that are from these storms here. So that's the Category 5 hurricane. And when you look at the losses from that Category 5 hurricane and the 20-year storm, which was the Category 2, those two scenarios actually had very similar damages in terms of the numbers with the sea level rise, with and without sea level rise. When we look at the Category 4 hurricane, because it's impacting the coastline so severely, and you're getting all 11 counties impacted at almost a maximum level, it had the largest impacts, and those impacts were up around $20 billion in terms of that hurricane. So it'd be a devastating hurricane for the Georgia coast, whereas the Category 5 and Category 2, in the way that they approach the coast, were on the lower end, say around somewhere between $2 and $4 billion for those two hurricanes. So the reason that we started with this as an initial assessment, the issue with these types of assessments is they don't really drill down and get to the specifics of what any one community is going to be facing. Certainly you would understand what's happening in those communities right along that Category 5 path, but what about the communities to the north or the communities to the south? Those communities wouldn't be expecting Category 5 winds. They'd be expecting something or Category 5 winds, they'd be expecting something much lower than that because they're further away from the hurricane path. And so in phase 3, we focused specifically on Tybee Island and Hinesville. And we wanted to look both at the current day risks from flooding and hurricanes in the phase 2, and then future risks for Hinesville and Tybee Island in phase 3. So we developed a strategy for completing the present day riverine and coastal flooding hazards to model, and then modeling also the impact of hurricane winds. We focused on riverine or river and stream flooding for Hinesville and the Hinesville area, and then coastal flooding and hurricane winds for Tybee Island. And then we wanted to look at green infrastructure potentials for flooding scenarios, and then mitigation scenarios, so building mitigation scenarios for wind. So we could see what the impacts of those actions would be on both current hazards, but also future hazards. And so HazardSimH, in conjunction with GIS analysis, were used to develop these hazards. So for Hinesville, in terms of the green infrastructure piece, we looked at just retention of about 10% of the existing water. And then we recalculated the stream flow. So what we're simulating here is not any one specific green infrastructure project, but the projects that would be implemented would retain about 10% of the existing water. For Tybee Island, our green infrastructure project was simulating developing an 8-foot dune, which was the current, at the time, strategy for Tybee, was to have a dune that was about 8 feet and then had all the measures in place that would be protective for Tybee. An 8-foot dune for Tybee Island, and see what the potential for that would be if that was around the island and reducing the amount of storm surge. And then for Tybee, we also simulated a 10% of the homes would have shuttering on them. After talking with different people within the community, they felt like that 10% would be a reasonable number of people that could potentially, just given some sort of incentive program or just through awareness projects, maybe 10% of people would choose to do some permanent shuttering on their structure. So when you're measuring risk, what we're trying to do here is not measure a single event. We're trying to measure statistical probabilities. And so typically we hear of things like the 100-year flood or 100-year hurricane. The better way to describe that is the 1% annual chance, okay? And so the equation for that is if you had one of these happen in 100 years, that means you have a 1% chance of that event occurring. And so we were doing that. We're modeling the 1% chance, 500 years the same way. That's the 0.2% chance of that flood or hurricane occurring in any given year. So you can have a 1% annual chance flood event in back-to-back years. I know Indiana did that in the mid-2000s, where they had 1% annual chance floods in back-to-back years. It just means that that's the statistical likelihood that you'll have that one flood event or have that one hurricane event. So because of the confusion of the terminology, we're going to stick to using percent annual chance rather than return period, but you can always go back and forth. So anytime you see 1% annual chance in this presentation, think of that as the 100-year flood or 100-year hurricane. So this is an example near Hinesville of the streams and rivers we were modeling within Hinesville, and the boundaries of the different flood events that we're looking at. So the light blue is where the 10% or 10-year flood would be, and then the 1% chance is where that would expand for the 100-year, the 1% annual chance flood. Now here's an example of the change in elevation or changes in depth along those same streams and rivers for the 500-year 0.2% annual chance flood with the addition of green infrastructure. So for along this whole area, you have places where you're seeing up to 3 feet's worth of lowering of the water within that stream and river. And 3 to 4 feet is a major, is a big number, because when you think about damages to a structure, it's that first 4 feet that you see the most damage within a structure. Once you get over 4, 5, 6, 7 feet, the amount of damage levels off because the building is already almost completely destroyed in terms of the amount of water and the damage that that will do. And then here's an example of the 100-year flood. Actually, this is the 10% annual chance, so the 10-year storm. And this is the change in the flood depths from those dunes. And so you can see there's been some significant changes in the flood depths. On the left-hand side is what that flood depth grid looks like without the dunes there. And on the right-hand side, you can see the changes in depths where you have a reduction of water throughout Tybee with that dune system in place. We also did the current day or present day hurricane winds for Tybee. We did category 1 through 4 hurricane winds. They were direct hit, landfall for Tybee, We made sure that everywhere on Tybee had the same exact wind speed. Because of the software, you'll notice there's a little bit extra land here to the south and west. We weren't just measuring the sort of the Tybee Island area itself. That's just an artifact of the software. It had to include the entire census tract. And so this other area that's here is a part of that census tract. So for this area, category 1 through 4 winds, it actually equates to the 30-year, 100-year, 200-year, and 700-year return periods. A category 4 hurricane for this particular area would be a lower chance event. It represents about the 0.14% annual chance event for a category 4 hurricane. So for the category 4 hurricane, the gusts can be as high as 179 miles per hour. And then that's what the gust was, not the sustained wind, but the gust that we modeled for Tybee Island for that category 4 storm. So for Hinesville, this is the reduction in losses. So if you look at the floods here, the 10, 25, 50, 100, and 500 year, so 10%, 4%, and so on. And you look at present day flooding, which is the blue curve, and then present day flooding with that reduction of green infrastructure is the light blue, or that cyan curve. You can see that there's a really big reduction, especially in the earlier return periods at the 10% annual chance, where we see a reduction of about $700,000 in terms of the loss there. We see similar but not as drastic reductions as you go up in the return periods. And partially that's because we're trying to mitigate against these, only removing the 10% of rainfall. When you get into the higher return periods, there's such a high volume of water in those cases, that small reduction isn't quite making as much of an impact as when you're in the smaller return periods. So this is the Tybee Island building losses, and you can see that there's been a major reduction in the losses there toward the bottom at the 10% chance. But remember, the dunes are only going to protect against that 10-year storm, or that 10% annual chance storm. After that, the 8-foot dunes, the water is going to begin to overtop those. And so when you get to the 25 and 50-year return periods, 4%, 2%, those dunes are no longer going to be able to protect against those storms. And so at 8 feet, you're going to see the same present day flood with the green infrastructure. Are going to have similar losses in those cases. Now for wind losses, this figure, because of the numbers that we have here, I'll just go ahead. So we estimated having about 10% of the structures reducing, and you can't actually see the gap there, but 10% of the structures are going to have those wind shuttering on them. And you can see as you get into the higher return periods, those make a bigger difference on the higher return periods. In the lower return periods, you don't see as big a difference because the wind damage is not as great. But as you get into the category 2, category 3, and then the category 4 storm, you see what the benefits are from having the shuttering because the wind speeds, of course, are going to be so much greater. So riverine flood damages remain the same throughout the flood magnitude, but the losses are going to increase as the flooding increases. So what we're saying there is the boundaries, as the boundaries were remaining about the same. There wasn't much expansion into the floodplain as we increased the flood magnitude, but the flood depths were changing dramatically across the floodplain. And so we can see those flood depths getting deeper and deeper and deeper, and that's why the riverine flood damages are then changing throughout time. The green infrastructure was most effective against the more frequent floods, so the 10%. So with the 10% annual chance flood, we had a 39% reduction in loss. It goes up, of course, as you get into the higher flood event, or it goes down, of course, the reduction does, as you get into the higher flood events, because there's just so much water that's there. So even at a 10% retention, we're seeing some pretty significant losses, loss reduction, just on that, especially on that lower return period. So we do not have any recent building construction or future building developments in this analysis. This is just the current building states that we had at the time of the analysis that we performed. So the dunes at 8 feet were designed for that category 1 or 10% annual chance storm every year. And so it only protected against that one. And so the savings for that one was about 82%, or about $20 million for that storm. So well worth having a nice dune system for that more frequent flood event. The one thing that to keep in mind is these dunes were constructed like a concrete wall, basically. We constructed them to say this dune was going to be 100%, would not fail. There were no breaks or holes in it, and there were no failures. So we're showing a perfect scenario in terms of the stability of that sand dune. And so again, this did not have any of the recent developments or future building developments. Those are going to be included in our future analyses. And so 10% of shuttering leads to a minor savings throughout Tybee Island. We have a 11% reduction, 2.1%, 1.7, but that's millions of dollars saved. So even at a 0.8% reduction, the amount of dollars saved is huge on that category for a hurricane. But the reduction seems small, but it's millions of dollars. You can see that in the figure where those higher return periods, the amount of dollars was quite substantial. So then in phase 3, this is where we're looking at future scenarios. We did 91 future scenarios between Hinesville and Tybee Island. We took the existing building stock and we looked at that for future scenarios. So what we're saying here is, if we don't do anything to our current buildings, they are sitting as they are, no new buildings, nothing. What do the future hazards look like for those existing buildings? And then we modeled a future building stock. We said, okay, we're going to be looking forward to 2080. And we want to take a look at, okay, if our communities continue to grow, we want to have a future building stock to show those future hazards alongside future buildings. We used future rainfall projections from the University of Wisconsin's Climate Center. We also got future storm surge information. We had sea level rise from Georgia Southern that provided to us that we could use in these analyses. We got information on impervious surfaces, current impervious surface area and future impervious surface area. And then we also looked at green infrastructure projects to help take a look at the mitigation potential. So for hurricane winds and storm surge, we did a 1 meter sea level rise. That was what was used for the future storm surge flooding. And we used an increase in hurricane wind speeds that follows the current and existing research. So right now, scientists in our building here at UW have determined that they believe there could be a 5 to almost 10% increase in wind speeds, which is a significant increase. It seems like a small number, but if you think about it, you could be going from a category 2 hurricane to a category 3 or higher, just with a 10% increase in wind speeds into the future. We also changed the forward speeds, and we also changed the size of the hurricane based on some of the research that we have today. For riverine flooding, we increased the stream flow based upon what is going to be changed with respect to rainfall in the future in the Hinesville area. We also had increases to impervious surfaces based upon what we believe is a reasonable estimate in the increases in population there within the Hinesville area. So the impervious surface and rainfall changes are what contributed to the changes in stream flow. So this is an example of the riverine analysis near Hinesville. The blue is today's 1% annual chance flood that we modeled. The pinkish and reddish areas, that's where that flood would expand into the future under our new scenario for the 1% annual chance flood. You can see the buildings that are in green, those are buildings that would be currently within the 1% annual chance flood. And then the purple buildings, those are the buildings that would be added to the potential future flooding that they may see in Hinesville, in the Hinesville area. So this is an example of the change in flood depths. We're here where we're looking at changes from sea level rise and storm surge for Tybee. That 1 meter rise in addition to the stronger hurricane, and this is that change in the 1% annual chance depth. So in both cases in the future flood studies for both Tybee and Hinesville, we saw some pretty large changes in the extent of the floodplains in both. So there's a lot of information on this slide. I'm going to walk through exactly what we're looking at here. And so this 9.40, that's the current rainfall estimate for the Hinesville area for the 50-year rainstorm, not flood, the 50-year rainstorm. So the 2% annual chance rain that you would expect for the Hinesville area. So our climatologists looked at future scenarios up to 2080, and we wanted at best case scenario. So if everything goes great with respect to our climate, we reduce some of the things that are going on with respect to the climate. What's the potential for a best case scenario for rainfall in the future? That's the 9.57 inches of rainfall. Then the 10.92 is the increase we would expect given all of the projections that we have. And so this is the number that most people would say, this is the one to plan for. It's the middle of the road projection. And then the final one is the worst case scenario. So that 9.4 jumps up to 12.75 in terms of the 50-year return period rainfall. So this is called the 25% best case scenario, 50%, the one that people could plan for. This is the one scientists are expecting. And then the 75% is a worst case. So things just go way out of whack and something crazy ends up happening. And this is the highest end. So this best case scenario projection, we only changed the rainfall by 1.8%, but that 1.8% led to a 24% increase in the average water volume within the stream. It also took our losses, our today losses, from 3 million to future losses, $12 million. That middle of the road projection, that was a 16% change in the amount of rainfall we're looking at here, but that was a 57% increase in the water volume. So if we look at our present damages, that goes from $3 million to $20 million. And then in our worst case scenario, a 36% change, that's a 116% increase in the water volume, and 3 million jumps up to 23 million in 2080. So this is what it looks like from a building damage count perspective. And if you just focus in here on the 1% annual chance, this is our present day, okay? And so the numbers did not change in our present day, but the dollar losses did. So the buildings that flooded, there was more water there, and so the losses increased when we looked at the present day versus the future condition. So then here's the best case scenario. The numbers in the middle, this is the analyses that we did for, between the existing buildings, and then the ones at the top are future buildings. So we modeled future buildings here, and this is the present day buildings here. This is a business as usual versus green infrastructure. So if there's no green infrastructure in place, our 94 buildings in the future jumps up to 328. If we implement green infrastructure, our 94 buildings currently damaged only jumps up to 266. So there's about a 60 building difference between doing green infrastructure in the future and not doing green infrastructure in the future. These two numbers are telling us what the potential could be if we added new construction in the area. Our 94 buildings jumps up to 450 under green infrastructure scenarios, and our 94 building jumps up to 535 buildings with no green infrastructure implemented. And so the two yellow bars here is the same thing, except here we're looking at that middle of the road scenario, and then the final, the light green and dark green, that is the worst case scenario where we're really jumping up the amount of rainfall. And so here, with nothing in place and a worst case scenario rainfall event, 94 buildings jumps up to 855 buildings. So this is the dollar losses. A similar thing is going on here. When you look at the present day, this is our present day flooding, present day buildings. So here we're sitting at something around $3 million. Best case scenario, we're jumping up to $10 million. Middle of the road scenarios, now we're jumping up into the 20 million, and then the worst case scenarios are up here, getting close to $30 million. So a major change from the $3 million jumping all the way up to $20 million for those areas around Hinesville. So this is coastal flooding for Tybee. Similar graphs here. We're looking at the future damages from sea level rise and stronger hurricanes. And I'm just going to focus in on one here. This is the 1% annual chance hurricane here. So we have 859 buildings that are damaged from the current flood. We look at future flooding with our existing buildings. That's in the reds here. Those 859 with the future flooding, sea level rise, stronger hurricanes, 859 jumps up to 1259 with green infrastructure and 1685 without the green infrastructure. Here we're building the dune a little bit higher to mitigate against the 1% annual chance hurricane event. This is worst case scenario where we're looking at this coastal flooding. We're going from the 859 buildings with future buildings here. So we're simulating what the expansion on Tybee could be from additional houses or development along Tybee Island. And so we're going from 859 to future hurricane events and building construction on the island there up to 2,800 buildings. So a significant change in the amount of damage. These are the curves that for the losses that we have. The 1% annual chance is the one I was focusing on here. These are the higher events that we have on the right-hand side. So here we're looking at somewhere around $20 million in terms of our current or present day losses from the 1% annual chance flood. If we look at future buildings being added and the intensity of the hurricanes getting stronger and the sea level rise, that $20 million jumps up to over $100 million under that scenario with the future buildings. So significant increase, 20 million up to over $100 million. And then if we look at these lower, this is the category 4 over here, we see an even more significant increase. This is the category 4 hurricane. This is what our current losses would be projected to be around. So around $250 million for that category 4. And under future conditions and that increased building stock, then we're looking at something close to $600 million. So quite a jump over 250 million. And this is the wind losses that we have here. Current winds are along the bottom. And then when we add that mitigation, even though the overall percentage of reduction is low, the amount of dollars saved is quite a bit when we look at those future buildings. So if you look at that blue line and orange line, we have a savings over, about $20 million or so just between those two, adding that mitigation, where 10% of the buildings are putting some sort of permanent shuttering on them and using them during the hurricane. And this is the damage counts. I'm not going to focus too much on this. We've seen these a few times, but this is what we're looking at in terms of the current wind with and without mitigation, and then the future winds when we have the mitigation of the 10%, and then this is future building construction added, and then the reduction that we have when we add that 10% of those buildings. So currently, present day, 2,800 buildings are going to have the moderate or higher damage, and then into the future, adding buildings, we're going to have far more. So why are we seeing some of these major and drastic changes along the floodplain? So we see these major, as we look at future flooding, major changes in the number of buildings that are constructed or that are flooded and the buildings that are damaged. And part of the reason that we're seeing this, and this is really true in coastal communities in terms of the way the flood hazard operates, is that we have a lot of construction, and this is all around, I'm not picking on Pooler, Georgia at all whatsoever. This is just one example. This is happening all over the United States. Kevin and I did a study to take a look at how prevalent this is, and it's extremely prevalent in most states, where we have buildings that are being built or they have been built adjacent to the floodplain. And so even though these buildings that I'm showing here might be elevated to a flood elevation above the existing floodplain, if we make any changes to that floodplain, so have a change in the amount of water, if this is, say, elevated 3 feet above this floodplain, but then that floodplain has more water in it, either from sea level rise or increases in precipitation, that is quickly going to then take and add these homes to the floodplain and the damage and loss scenarios. And so this is very common throughout the United States. We see it to be more of a problem in coastal areas, and the reason it's more of a problem in coastal areas is because a coastal flood is going to impact everything in terms of the storm surge coming on, and it's more of a continuous surface of water. Whereas riverine flooding sometimes is confined to a channel, the storm surge flooding is not confined to a channel. So future condition analyses are showing a worsening risk to these areas. I think some communities in Georgia have already experienced this. I know Hurricane Matthew, some of the rainfall from that was pretty significant in places along coastal Georgia. We've also had a number of hurricanes over the past 3 years that have impacted certainly the coastal communities with rainfall, erosion, and then also some flooding. And so I think we're seeing some, at least in recent years, this worsening risk in some of these areas. It was important for us in our study, and it's important in general to look at a wide range of potential scenarios versus any one specific scenario when you're making decisions. So you want to take a look at, we have 91 cases here, but communities want to look at a multiple set of scenarios. There could be scenarios that are trigger points, and so your floodplain might be holding water pretty well, but then at a certain flood elevation, all of a sudden that floodplain begins to magnify itself and turns into something that spreads across the community much wider. Let's say that could be at something like 20 feet, then all of a sudden at 20 feet, it's a trigger point to then add a lot more buildings. And then options exist for mitigating that risk. We looked at a couple of ways to do that, several ways to do that in these communities, looking at the retention of water. What would happen if you didn't have additional impervious surface or less impervious surface, looking at dunes and what the impacts of the dunes would be. But it's always important to, as a first step, what we were doing is really in some ways a first step, taking a look at where the risks are, what are some of the problems, and then start thinking about actions now going into the future, and then taking out a magnifying glass and then really zooming into the areas that we were projecting to have the highest damages and losses, getting that magnifying glass out and really sort of looking at why those things are happening. And then again, just looking at specific actions that could help reduce the amount today and into the future with respect to losses and damages. All right, so I'm gonna turn this back over to Kelly, and she's gonna talk about what the next steps are gonna be for coastal Georgia.
All right, great. Thank you so much, Shane and Kevin, for providing a very quick summary of what was a tremendous amount of work that was completed for this project. I want to quickly mention some of the associated work that's being completed by other partners, as well as fill you in on some upcoming training opportunities. And the next slide. So all of the tools and resources I'm going to mention that are related to this project are going to be posted online at this website. Please check back often, as we are just now beginning to populate the site, so some of these documents and tools will be uploaded in the next few weeks. But this is just a quick highlight of some of the other products that you'll be able to find there. Kevin and Shane and other researchers at Polis Center and UW also worked on a great 2-page infographic document. It is a great quick guide to reference when looking for big takeaway messages. That is a screenshot on the left there. Also, we have partnered with UGA's Marine Extension and Georgia Sea Grant to create an adaptive stormwater management plan for the city of Hinesville. So this plan will help them identify the potential next steps that they can take with installing particular green infrastructure practices in the watershed after seeing the long-term benefits that were identified by this study. And then also we partnered with UGA's Carl Vinson Institute of Government, and they've created a wonderful comprehensive coastal resilience planning guide. This has a lot of the next steps that Shane was referencing and how to go about implementing some policies to tackle some of these issues. It will also include a suite of model ordinances and guide communities on how they can go through community rating system credits. So this is in some final edits right now, but we will be putting that up on the website very soon. And then not pictured here, we've also partnered with an economist at UGA to explore a more detailed cost-benefit analysis of installing a particular green infrastructure practice on the ground in the Hinesville area. And then we're also continuing to partner with Georgia's Coastal Regional Commission, located here on the coast in Darien. They're assisting with data management to help us ensure that we can share all of these meaningful results with communities that are interested in possibly replicating this type of study. The CRC is also working on compiling a lot of these results and tools and resources that I'm showing you now into an online story map. And we hope that this can become a great one-stop shop for accessing data and learning, continuing to learn about this project overall. All right, next slide. And lastly, we will be offering additional and more detailed technical trainings on this project in October. You can see kind of a screenshot of what the trainings will entail, as well as the dates. You can write these down. We're also going to be posting all of this on that website as well. These are going to dive down a little deeper into the details of the study, and then the project workflow HAZUS training will be tailored to that HAZUS technical user as well. And then, stay in touch, because in 2021, hopefully when we are all able to be together again in person, we'll be doing some more in-person stakeholder-specific outreaches throughout the year. So please check the website often and feel free to reach out to Jennifer or I at any time. This last slide here, Shane will have our contact information. And with that, I guess we'll go ahead and move over to the Q&A part of the webinar. I wanted to thank everyone for your time today, for joining us. We're really thankful to be able to talk about this project after many years of a lot of detailed work. So we're very excited to move into this phase of our strategy. Again, please reach out with questions at any time. And if you have questions today, please go ahead and type them into that chat feature, and I will go through and ask them in order that they're received. I don't see any yet,